Hello, this video will cover section 5.3, the Poisson probability distribution. So just like with the binomial probability distribution, the Poisson probability distribution has some things that we need to keep in mind. So a Poisson probability distribution applies to occurrences of some event over a specified interval. The random variable is the number of occurrences that happen over the interval. The interval can be time, distance, area, volume, etc. So this interval is actually a continuous variable, but the random variable, we're just counting the number of occurrences, is a discrete variable. The other requirements of a Poisson distribution are the occurrences must be random, the occurrences must be independent of each other, and the occurrences must be uniform over the interval. Technically, all three of these are, besides the first one, picking random is easy enough, but making sure that they're independent or that they're uniform, you can kind of almost just assume those last two. So the notation, we'll just say x is poise, lambda. This upside down y is the Greek letter lambda. Now you'll notice that it only depends on one number, where the binomial distribution depended on two numbers, n and p. Well, if x is Poisson with lambda, then the probability that x equals m is lambda to the m power times e to the negative lambda divided by m factorial. So the few things we have to talk about is e is just a mathematical constant like pi. E is approximately 2.71. And you will just be using the button on your calculator for that. Then the other thing is this exclamation point means factorial. That will be located where your NCR function was. So on the Casio, you'll press option, press F6 until you see the prob option, which I believe will be F3, and then factorial is F1, the first exclamation point. On the TI calculators, TI-83 and TI-84, sorry, you'll press the math button, go over to prob, and then you'll see the exclamation point on one of the options. I don't remember exactly which one right now. And then on the TI Nspire, near the bottom right hand side of your keyboard, there's a button with a question mark on it. When you click that, it actually gives you a pop-up menu with a bunch of other options, with the exclamation point being one of the options. If you have trouble finding the factorial button on your calculator, please let me know as soon as possible. Anyways, what does lambda even mean? It's the mean number of occurrences of the event in the interval. Well, since lambda is the mean, that makes sense that the expected value is just equal to lambda. Nothing surprising there. The surprising part, though, is that the standard deviation is just the square root of that number. So now that we have our formulas for Poisson probability, we can do some examples. So in a recent year, there were 4,229 births at a New York University Langone Medical Center. Assume the number of births each day is uniform. Find the mean number of births per day, then find the probability that on a selected day that there are exactly 10 births. So here is where they gave us the average in years, but I'm looking for the probability of a day. So this is common for Poisson distributions, where it gives you the average in one unit of measurement, but you need to convert it to another unit of measurement. So here, to convert years to days, our lambda will equal 4,229 divided by, and we'll just use 365. As I was saying 5, I wrote a 4, but 365 days in a year. So 4,229 divided by 365. So we get about 11.6 births per day. So then to find the probability, well, that tells us that X is Poisson 11.6. Now the reason why it's Poisson, we have an interval of time. It told us it's uniform. If we're talking about births, we'll assume they're independent, and we're selecting 10 births, so we'll assume they're random as well. So we meet all the conditions. So then the probability that X equals 10 is 11.6 to the 10th power times e to the negative 11.6 power all over 10 factorial. And I'm getting 0.1114. And that's it for example 1. Now for example 2, the recent rate of car fatalities was 33,361 fatalities per 2969 billion miles traveled. So here again, we're talking about distance traveled, specifically 2,969. Find the probability that the next billion miles traveled that there will be at least one fatality. What does the result indicate about the likelihood of at least one fatality? So here again, it's not really a change of units, but they told us for 2,969 billion miles, and we really just want, even though it didn't say it, we just want 1 billion miles. So to find lambda, we take that 33561 and divide it by the 2969. That'll convert from 2969 to 1. Which is 11.3. So then X is Poisson 11.3 because it meets all the requirements. Well, then the probability that X is less than or equal to 1, because that's, at least 1, means greater than or equal to 1. Now here, because there's not a fixed number of trials like there was with the binomial, greater than or equal to 1 means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Because there's not a fixed number of trials, it technically goes on to infinity. Now, infinity isn't practical here, but there is no definite end that we can pick for a Poisson distribution. So here, I definitely do need to use the complement rule. So 1 minus the probability that X is less than 1. And since X is still counting something, it's only whole numbers, so this is the same thing as 1 minus the probability of X is equal to 0. So that will equal 1 minus 11.3 to the 0 times e to the negative 11.3 over 0 factorial. Now, this one's going to be a little bit difficult to type in because a lot of people type 0 factorial in incorrectly. So I'm actually going to simplify this before typing it in. First of all, I'm hoping you remember that anything to the 0 power is 1. So that's 1. And then a new rule, which you may not have known before today, is that 0 factorial is 1 by definition. So then this becomes 1 minus e to the negative 11.3, which is 0.99999. Now notice how I didn't round it to 4 decimal places, because if I would round to 4 decimal places, it would be 1.00. So I went one more decimal place so that it wouldn't be exactly 1. So what does this result indicate about the likelihood of at least one fatality? It indicates that at least one fatality is almost certain. And then the last example for these notes, example 3, is during a 34 period, there were 56 cases of a particular disease in one country. Assume that the number of cases of the disease during a year follows a Poisson distribution, so it's just telling us it's Poisson, with lambda equal to 64706. So since the problem gave us 5 decimal places, you should keep all 5. This the end of it, yeah. So it says construct a probability distribution table. So remember a probability distribution table. And here I'm going to make it vertical instead of horizontal. Is x and then the probability of x. Well, x is 0, 1, 2, 3, 4. And as we were saying before, it technically goes on forever. So I'm going to have to calculate the probability of each one of these separately using the formula lambda to the m times e to the negative lambda over m factorial. But since we know what lambda is, this is 1.64706 to the m times e to the negative 1.64706 divided by m factorial. Now, you can do this one by one, but I would recommend using a table to do this, where you would type this all in list 1. And actually, I'm going to go a little bit further than 4. I'm going to go at least to 10. So in list 1, I typed in the numbers 0 through 10. Now in list 2, I want to type this formula. So to help you, remember m is actually our list 1. So we need to go 1.64706 to list 1 times e to the negative 1.64706 divided by list 1 factorial. And you should probably put parentheses around there. So that's what we're going to type in for the formula for list 2. And don't forget the parentheses around the denominator as you're typing this in. So when I do that, I get 0.1926, 0.3172, 0.2612, 0.1434. Now I gotta scroll down. 0.059. 0.0194. Now on my calculator, it's going to be different per calculator, but it says this for the next one. Remember, this is the same thing as 0053. Now my next one is 0.0012. 0.0003, and then 9 becomes 0.00005. So for all intents and purposes, I could have stopped around 6. Even though it technically goes off to infinity, I hope you're noticing the probabilities are getting smaller and smaller and smaller to the point where it's basically going to be 0. So this is how you can do a probability distribution table for a Poisson variable without going to infinity. You just stop when the probabilities get small enough. The other thing I want you to think about is if we were going to do a histogram, like it starts out 0.19, then it goes to 0.3, then it comes back down to 0.26, and then 0.14, then 0.5, and then 0.1, and then less than that, then less than that, and less than that. So we definitely get this right skewed distribution. We didn't look at the distribution for a binomial variable, but binomial variables have multiple distributions. They can be normal, left skewed, or right skewed. Poissons are always right skewed. And that's it for section 5.3.